So good morning everyone. Myself is Dr. Azit. I'm faculty from Department of PhD at Presidency University. So we'll start our third lecture. So as I said that we'll start the architecture of 8051, and in the last class we studied about so here we discussed called something called fetch, upward fetch, decode, and execute. Okay, we studied about these three things. That was upward fetch, upward fetch. Studied about upward fetch, decode, and execute. So we studied about these three things that is actually required. Okay, so we saw that whenever we write the code gets stored in the memory chip. The code gets stored in the memory chip. So here our program is stored. Okay, that is, and here this is our memory chip. So our memory chip is this one, and this is our processor 8 processor. This is our processor, microprocessor. So what happens? I said that this my memory chip and processor, they are connected with electrical wires which are called address bus, okay, data bus, and control bus. Okay, these are the different buses that is actually required to for the communication between the processor and memory chip. Okay, so whenever we write any code, no, suppose that we have written this program. Okay, let's say we have written here one program to add two number. Okay, that is 25h with 45h. Okay, so I'm assuming that you people know a little bit about the instruction, or else we are going to start the instruction in the second module. So what is there is that we are store this number in any one of the register. Let's say A, accumulate. Okay, this in register B. Okay, using move instruction. So I'll write here move A comma as 45h. Then I'll write here move B comma has 25h. Okay, and then I will write here add A comma B. Then I will write here end. Okay, then I will write here end. So according to now, what is there is, okay, every instruction has two parts, which is opcode and operand. Okay, so here we have part which is opcode and operand. Though there are other things also, but these two are important: opcode and operand. So opcode means operation code. Opcode means operation code. Okay, and operand means data over which operation has to be done. Data. Okay. So here see this opcode. Okay, we have this move is the mnemonics to move data from source to destination. Okay, so here the move instruction works something like this. Move. Okay, we have two operands. This is called source. Okay, and this is called destination. So here the data goes from source to destination. Okay, this is the purpose of move. So we'll study about the instruction later on. So in this case, we know that this 45 is actually source, okay, and this is accumulator, which is destination. So your data 45 will be getting stored in the accumulator register. Similarly, this 25 is source, and this is B destination. So your data 25 will go in the B register. Now this move A is opcode, and this is your operand. I mean, basically move. Okay, you can say move is the opcode, this is your operand 1, this is your operand 2, so this is your source operand, this is your destination. Okay, so this opcode, okay, this opcode is for the move instruction. Similarly, for the add instruction, the opcode is this one. Okay, add. So as the name suggests, operation code. Okay, that means what is the operation? Here the operation is moving the data. Here the operation is adding the two data. That is adding two operands. Where are the operands? In the register A, register B. Okay. So when we write this instruction, no, they are translated into machine code. Okay, machine code is basically code which is composed of zeros and ones. So for example, move, okay, may have move a comma move a. Okay, that is move a may have opcode something like 0, 0, 1, 0, 1, 1, 0. I'm assuming that this is the opcode of move a instruction. Similarly, this 44.5, which is a hexadecimal number, will have this in the binary form 0, 1, 0, 0. Similarly, 5 is 0, 1, 0, 1. Okay, we are writing. Similarly, for the move B also, let us say that 1, 1, 0, 0, 0, 0, 1, 1 is the opcode, and then 25 is 0, 0, 0, 5 is 0, 1, 0, 1. Like this, our ALP, our ALP is translated to machine code. And I told you that there is a software which does this, which is called assembler. Okay, assembler is the, okay, software that will convert the ALP into the machine code. Fine. This is how it actually works. Now, this machine code will be getting saved in the memory chip in each location. So we have different memory locations here. In each location, 8-bit data is stored. It's not predefined, but for the 8051, it is like that only. So the first instruction opcode is actually 8-bit. So all these are 8-bit. Okay. In each location, 8-bit data can be stored. So one, so like this, 1, 2, 3, 4, then 5, then 6, then 7, 8. Like this, 8-bit data can be stored in each location. Okay, 8-bit data, and this data can be either our opcode or operand. Okay, operand. So this 0, 0, 1, 0, 1, 1, 0, 0, which I'm assuming is, I mean, opcode is having fixed machine code. Okay, I'm just, we can't remember these things. I'm just taking the example that let us assume that this 0, 0, 1, 0, 0, this is the opcode of your move A instruction. Similarly, 4, 5 will be stored here. That is 0, 1, 0, 0. 5 is 0, 1, 0, 1. Similarly, the next, so in this two location, our move A comma has 4, 5 instruction is saved. Similarly, in the next two location, the next your instruction move B comma has 25H will be saved. Okay. Likewise, these instructions are saved in the memory chip in the form of zeros and ones. Okay. Now, here the processor is going to perform this execution. Okay, what is that execution? 25 plus 45. Okay, this is hexadecimal number. So these two numbers are supposed to be added by the processor. Okay, you may get some answer, that is fine. That is 5 plus 5 is 10, which is 8, and then 4 plus 2 is 6. So 6AH is the answer. So this should be done by the processor. So let us, I mean, in the last class, I think I have explained also that how it actually works. Okay. So uh, here, so in this case, what is happening is, uh, we know this will be done in the three phase. That is fetch, okay, fetch. Second one is decode, and then third case is execute. Okay. So fetch means acquire. Okay. Decode means interpret, and execute means perform. Fine. So in this case, uh, this instruction will be faced inside the processor. Okay, so the processor, and now one more thing is there, that each location has certain address. Okay, for example, this may have address 000h. Okay, this next may have address like 001h, 0002h. Okay, 00003h. So these are again hexadecimal numbers which are 16 bit. For example, this 0003h. Okay, this is a 16-bit address. That is, this 0 is 1, 2, 3, 4, and this 0 is 1, 2, 3, 4, and then this 0 is 1, 2, 3, 4, and finally this 3 is 0, 0, 1, 1. So this is a 16-bit address. 16-bit address in case of 8051. Okay, so for each location the 16-bit addresses are assigned. Okay, now what is happening, there is a register inside the processor which is called PC, program counter register, which will store the starting address, and not only starting address, all the addresses from where the instruction has to be fetched. So the starting address is 000h. So this address from the PC will be loaded on the address bus. Now this address bus being a 16 bit, a 16 electrical wires. Okay, will carry individual bits, that is 16 bits, and this address will be received by the memory chip here. Now there is an address decoder circuit which is not displayed here. Okay, ideally something like this is memory chip. We have here address decoder circuit, address decoder circuit. In fact, the address decoder circuit is inside this processor one, memory chip one, decoder circuit. So which is basically composed of logic gates. So this address first comes in the address decoder circuit, and then this address, from this address, okay, the data is whatever opcode was there. So that opcode will be loaded on the data bus, will be brought inside the processor. So the first instruction, that is 00010, that is opcode of move instruction, is brought here. Okay, that will be saved in the instruction register. From instruction register, this 00, that is 001 01100, this was the instruction. Okay, that is this is the opcode of the move A instruction that gets stored in the IR. When it is brought from the data bus, it will be getting moved in the instruction decoder circuit. Okay, instruction decoder circuit is there, which will decode the meaning, and then what is the execution is? Execution is that A should be saved with 45h. This is execution. So fetch, decode, execute. These things happens. But the thing is, this doesn't happen, okay, randomly. Okay, there is something inside a processor which is called oscillator. Okay, so we have here oscillator circuit. Oscillator is there. Oscillator is there. The purpose of this oscillator is to generate a clock signal. Clock signal is periodic on-off type of signal, right? Like this. So this clock signal is generated. Okay, this clock signal is generated by the oscillator for the purpose of timing. For the purpose of timing. Okay. So what is happening? This is the microprocessor, okay, inside which we have on-chip oscillator. Okay, for the production of this clock signal, and here our memory chip is there in which our program is stored. Now what is happening, what I said is that we have buses which are connected to this one. So we have data bus. So data bus will be from processor to the memory. Okay, this is data bus, oh sorry, address bus, address bus. Then we have data bus which is bidirectional, the data can go in both ways. So we have that data bus, DB, and then we have control bus which is unidirectional again, okay, CB. So what I said that in the memory chip we have different locations. Each locations can store 8-bit opcode or operand. So from here those opcode and operand will be brought inside the processor to this three steps, that is fetch, decode and execute. These three things will be performed here, that is fetching, then decoding and executing. But this fetch, decode, execute is not actually happening, randomly. This actually happens with respect to a clock signal. So this clock signal is a periodic on-off signal. Okay, and periodic means there will be a time period. Okay, This is one complete cycle. That is one off and one off on period is actually one complete cycle. So this is one time period. Okay, and the f, which is frequency, is 1 by t. Okay, so our 8051 microhertz, sorry, 8051 microcontroller is having not fixed frequency. It depends upon the variants that which one we are using. Okay, so the frequency ranges from 10 megahertz to 40 megahertz. Okay, so whenever you are going to buy any laptop, you should see the frequency. You might see the features of your computer. In that case, it is given that if the frequency is 3.2 gigahertz, 3.1 gigahertz, and so on. Okay, so that is the frequency of your this processor. At what speed the processing will take place here. Okay, that frequency is actually given in the your system properties. Properties. If you open the computer, you see the properties. This frequency will be displayed. So I was saying that this 8051 frequency, for 8051, the frequency is different for the different version of your microcontroller. Okay, it ranges from 10 megahertz to 40 megahertz. Okay, now, how what I was saying that this fetch, decode, execute. Okay, this operation actually take place with respect to this clock signal. Okay, for example, let's assume that this frequency is 10 megahertz. Okay, let us say that the processor that you have, microcontroller that you have purchased, is having 10 megahertz frequency. So this is the frequency. Then accordingly, time period will be 1 by f. So let us calculate this time period. 1 by f is 10 mega means 10 to power 6. Okay, so this comes zero point 0.1 microsecond. So this time period is zero point 0.1 microsecond. Another time period will be there, that is from this on to this off. It is also t equals to zero point 0.1 microsecond. Okay, zero point 0.1 microsecond. Then another time period is there, which is also zero point 0.1 microsecond. Now, what is happening? No, this fetch operation. Okay, let's say, I mean, just assume that the fetch operation is taking zero point 0.1 microsecond. So this fetch will be done in one time period. Okay, here. Then once this fetching of instruction has been done, okay, from the memory, the instruction has been fetched here. That is move A. Okay. Now, second thing is decode. So in the decode, it will. So, okay, you know that this move A is not brought as it is. It was actually 0 1 1 0, whatever I have written here, 0 0 1 0. That was the opcode which was brought. So decode means what is the meaning of this one? That is interpretation. Okay, so that interpretation will be done in the second clock cycle. Let's say in the second clock cycle, it is doing the decode operation. Then after this decode, it is going to do of execution. What is execution? The register A should contain 45H. So register A is inside this microcontroller. That is also 8-bit register. So that register will be loaded with this 8-bit data, that is 0 1 0 0, and then 5 is 0 1 0. Okay. So like this 8-bit data, that is 45H, it will be stored in the register A, that is called execution. So this execution, let us say that this is taking another clock cycle. So you can see to fetch, decode, execute one instruction, it has taken this much time. Okay, that is 3t. That is 3 into zero point 0.1 microsecond is 0.3 microsecond. So in zero point 0.3 microsecond, it has executed the first instruction. Similarly, the next instruction may be executed in the next zero point 0.3 microsecond. Okay. In our microcontroller, this t time period is called, uh, this is also called state. Okay. So in the terms of microprocessor or microcontroller, this time period is called state. Okay. So the first state, second state, third state, and so on. So like this, our instructions are being fetched, decoded, executed according to this timing, which is actually the clock signal. Okay. And how this clock signal is generated? Using oscillator, on-chip oscillator. Okay. So we have a on-chip oscillator inside the microcontroller that will generate this clock signal. Fine. So having gone through this concept, we are now ready to understand the block diagram of our microcontroller. Okay, so here a rough diagram is given. In fact, proper diagram is there. So you see here that we have, if you see here, there are different blocks. Okay, the most important block is the CPU, where the CPU is central processing unit. So our microprocessor, okay, which is actually doing that operation, is that fetch, decode, execute, and where from it is doing from the memory. So when we write our program, the program gets saved in our ROM. Okay, this is the ROM, also called program code. So our code or ALP is saved in this memory chip, from where it is fetching, decoding, and executing. Okay. So now you can, I don't need to show these arrows because you can see these arrows are already there, which are buses. Okay, these buses are actually the electrical wires which is connecting all these in chips with each other, with one another. Okay, and this whole, okay, now this whole this, this whole this whole is one chip, one IC, which is your 8051. Okay, microcontroller. So inside 8051, all these on chip are there. That is, microprocessor chip is there, which is connected to this ROM chip, which is also connected to the RAM chip, which is also connected to this timer. Okay, timer is used to generate the to either generate the delay, okay, or count the pulse. Okay, we'll study this in the third module. Count the pulses. So this will generate the delay or time count the number of pulses. This is on chip RAM in our 8051. The on chip RAM is 128 bytes. Okay. This is ROM, which is 4 kilobytes in our 8051. We have interrupt control. Okay, for the controlling the interrupts, total we will see that there are 5 interrupts here: INT0, INT1, okay, and then TF0, TF1, and then we have R1, okay, D1, okay, for receiving and transmitting the signals. So we have these interrupts which are controlled by interrupt controller here, and then this is the oscillator which is shown here. Okay, this oscillator we use to generate a clock signal, that as just now we have seen. Then we have a bus controller, okay, which will control the buses. Okay, then we have 4 I/O ports. 4 I/O ports means, you see, the microprocessor is connected to the see, this microcontroller is connected to the external devices. Okay, external devices like any, it could be like any external devices, keyboard or something, whatever you can take. Okay, so those devices are connected to microcontroller not directly, but but they are connected through ports. Okay, so it is something like this, that this is the microcontroller. Okay, okay, the microcontroller actually is connected to different devices. Let's say this is device 1, okay, this is device 2, device 3, and so on. Now, these different devices are operating at different frequency, different voltage, and they have different power consumption also. Similarly, this also may have different frequency, different voltages, different power. Okay, so what is that? The problem is that each one of them is having their own character specifications. Okay, but the microcontroller cannot deal with so many devices having different features. Okay, for this purpose what we do is we use here ports, IO ports, which is called input output ports. Okay, this input output ports is for the compatibility issue. Compatibility issue. Okay, compatibility issue means this device 1 which is operating on the different voltages will be made to operate this microprocessor. Okay, then this another device which is operating on another voltage will also be made compatible to work with this microcontroller. Okay, so this IO ports actually receives the data from the IO device, give it to the microcontroller, or it may receive the data from the microcontroller and give data to the IO devices. That is why it is input output device. Input device means the data is coming from the input device. Okay, so data is coming means inside the microcontroller. So when the data goes from input device like keyboard, okay, so we know that keyboard is input device. So here this input device, the data goes from my, remember this one, the data will go from the input device to the microcontroller. But if it is output device, then the data will go from microcontroller to the output device. Let's say we have here LCD display or LED display. Okay, LED display. Then the data which has to be displayed will come in this LED. Okay. So this is output device here. Okay, this is output. So that is why I'm saying this IO port is there. The purpose of this IO port is used to receive the data, transmit to the microcontroller, or receive the data from the microcontroller and transmit to the output device, and so on. Okay, so for this purpose, we have this IO ports. In microcontroller 8051, we have total 4 ports. We have 4 ports of each 8 bits. Okay, so that is port 0, okay, port 1, port 2, port 3. Fine. All these are 8-bit ports. 8-bit ports. So 8-bit ports means we have here 8 pins 1, 2, 3, 4, 5, 6, 7, 8, port 0. We have another 8 pins for port 1 and so on. This is 8051 microcontroller. 8 pins and so on. So total there are 4 ports. Okay, each ports are used to interface with the outside world. Fine.
So we have seen that this, okay, so various blocks we have seen here. So now let us proceed to the next topic, which is different registers and different register banks of 8051. So here we know that registers are used as temporary storage device to store the data temporarily. Okay, so in every microprocessor, in every microcontroller, we have a fixed number of registers. Okay, so in our 8051 microcontroller, we have some very frequently used registers. Among them, this register A is there. The name of this register is A. Okay, A is accumulator. Okay, A means accumulator. The full form is I bus. Okay, the full form is the accumulator. So this is an 8-bit register. Okay, 8-bit register, and it is very important registers. Okay, we'll see that this register is used to store the final sum of your, I mean, final result of your arithmetic or logical operation. So whenever you are going to perform any arithmetic operation like addition, subtraction, multiplication, or any logical operation, one of the operands should be definitely into the A register. Okay, that one of the operands should be definitely stored in the accumulator register, and the final answer will also get stored in the accumulator register. For example, when you suppose that you want to add 45H, okay, with 25H. So here definitely one of the data should be in the register A, and this another data you can store in any other register like register B, okay, which is also 8-bit, or R0, R1, R2, okay, up to R7. These are also 8-bit registers. So you can store another operand in any one of these registers. Okay, that is not a very significant issue, but the one of the operand is should be definitely in the A register. So that's what I will do is I will write here move A comma has 45H. Then I'll write here move, okay, B comma has 25H. Then I'll write here add A comma B. What is the meaning of this one? A, see here, this is source, this is destination. In the add, we have two operands. Okay, so this B is the source register, A is the destination. So what is the meaning? Destination is equals to destination plus source. So that is A is equals to A plus B. So the value of A is, here we have seen that A is containing 45H, B is containing this 25H. So this 45H will be added with 25H. Okay, the result was 6A will be stored in the A. This is the importance of register A. The register A is always destination and it holds your final answer. Now this DPTR is a 16-bit register, okay, which is called data pointer register. Okay, the data pointer register is actually used to, okay, to store the final sum of your arithmetic or logical operation. So whenever you are going to perform any arithmetic operation like addition, subtraction, multiplication, or any logical operation, one of the operands should be definitely into the A register. Okay, that is not a very significant issue, but the one of the operands is should be definitely in the A register. So point to the address. Okay, we'll see this instruction when we'll be dealing with the move X instruction and move C instruction. Okay, in that case, we'll see that how this is used to point to the address of the externally connected memory chip, ROM and RAM. Okay. Then we have another register which is called PC. PC is very important register which is called program counter register. Program counter register is a bit register and it is actually used to point to the address of the next instruction from where the instruction has to be fetched. That we have already seen in the some examples that PC was output 0000 starting address, and then from that address your either data or opcode was fetched from the memory chip and it was processed by the processor. Okay, so this PC is used to store the address. Okay, it is used to store the address of instruction. Then one of the most important register is the flag register. So in 8051, this flag register is called program status word register. Okay, this is the 8-bit register. So this program status register is used to reflect the condition. Okay, the condition of any arithmetic or logical operation. Okay, for example, after adding the result. Okay, so for this purpose, I'll show you here. Okay, that is this one. Uh, okay, so here, what is happening? This PSW, okay, this PSW is very important register. PS program, okay, program status word, program status word. This is 8-bit register. Okay, so 8-bit is let's say 1 bit, 2 bit, 3, 4, 5, 6, 7, 8. So this 8-bit register is there. Okay, and here let's say this is our 8-bit register. So here we have already defined bits are there. Okay, for example, P means parity. Then this is dash means not defined. It is not defined means in future it will be used for some purpose. Okay. Then we have OB. Okay, OB. Then we have this RS0 and RS1. RS0 and RS1. These two bits are very important. We'll see where it is used. Then we have F0. Okay, we have F0. Then we have here AC, AC and CY. Okay, so we have here auxiliary. AC means auxiliary and CY means carry. So this is auxiliary carry. Auxiliary carry. This is carry. Okay. Then we have this parity. So what is happening? Suppose that you are adding two numbers, subtracting two number. Okay, so let's say you are subtracting 4 minus 4 using those programs. So your answer is 0. Now how the microcontroller will know that answer is 0? Or let's say we are adding this 4 plus 4. Okay, so 4 plus 4 is 1, 0, sorry. Let's say I'm adding 8 plus 8. Okay, 8 plus 8. So 8 plus 8 is this number. That is this number. Let's say I'm adding this number. Now 0, 0, 0, and then 1 plus 1 is 0, and then 1. This extra bit is called carry. Okay, this is called carry. So whether my answer is 0, okay, whether there was a carry generated or not, or let's say I'm subtracting 4 minus 5, okay, then I'll get a negative answer here, okay, or similarly I may get positive answer, or after doing any one of these operations, let's say I'm adding 1 0 1 0 with another 1 0 1 0, then 0 plus 0 1 plus 1 is 0, or carry. So how many ones are there? Okay, here you can see it. There are one. Okay, single one. Single ones. Okay, single ones. So single ones means odd number of ones. Okay. So in this case, Whenever you are doing any arithmetic or logic operation, okay, and if odd number of ones are generated, that in that case this parity bit of the PSW register, okay, this is PSW register, will become 1. So this parity bit will become 1 to indicate that odd parity is there in the final answer. Okay, now where these are used, I'll show you with an example also. Now this is called overflow. Overflow occurs whenever you are doing operation on the signed number. Okay, on the signed number. Then these two bits are used to select the register bank. Okay, these two bits are used to select register bank. Then this F naught is again reserved for the future. Okay, this auxiliary carry is generated whenever we do arithmetic operation, and the carry is generated from bit D3 to D4, and this whenever the carry is generated from bit D7 to the next bit. Okay, so we'll study from here in the next class. Okay, so here we'll stop. So here we'll stop. Thank you.